let's get these started. Okay, so I'm gonna drag this over here, and I'm gonna drag this over here. This is one of my latest creative coding projects, and I figured I should do something that is educational. Okay, and this is around sort of antibiotic resistance simulation, the sort of simulating the evolutionary pressure, and essentially it's designed to make some evolutionary logic sort of visible. This is, of course, in the context of antibiotic resistance, so that's sort of grounded in some ideas like mutation, selection, gene transfer, and so on. But this is not meant to be an accurate prediction lab simulation. And of course, antibiotic resistance it's been a problem. It's been a problem, and it's actually an urgent global public threat. So, anyways, this very simple hub has three major components. So you have these control panel, if you will. This is our petri dish, and then you have, on the other hand, this stats panel, we could call it. And we have a strain called Basilicus stubbornus. There's really nothing like that, but this is just something I came up with for these projects. So in essence, what you have is you can essentially simulate how sort of these cells, these bacteria cells, if you will, multiplying, and how resistance is actually emerging. And you can also place in these antibiotic discs and just sort of clicking on the petri dish, and then just to simulate what happens when you have these sort of external pressure in this sort of ecosystem. So I'm going to just mention very briefly what some of these steering wheels are. This is just mutation is the genome stability, so the probability that a bacterium would develop resistance when dividing. Growth rate is, of course, how quickly the population actually divides and grows. Lifespan is just a natural lifespan. In my simulation, this is just the frames. So a cell dies of old age once it reaches this limit, 800 frames. And if I recall correctly, I think I have about 60 frames in a second. I'm not quite sure about that. But anyways, this is just a simulation of the lifespan. This is the capacity that our dish can hold, so you can tweak this. The strength of the drug, this is simply how large these discs are. I think the default is. So how large can we actually make these discs? And this motion is essentially to speed up bacterial movement. So if I play this, if I increase it, so you can see that the motion is actually increased, just sort of to speed up the experiment. So let's go back to the defaults settings. Okay, so I think what I'm going to do here is, and on this side that you have the stat, you have the name of the strain, the status, the frame. This is the percentage of the resistant strain that you have at any particular time. These are the numbers, and of course you have this. I'm going to talk about this later. This is the horizontal gene transfer. This is a transfer of resistance through sort of what we call pilus. But more on that later. So I believe what I should do now is let's just run one experiment, and we're gonna set up a lab whereby we're gonna have a limit of 400 frames. So that's gonna be the lifespan we're looking at. So at 4,000 frames, this is going to stop. So without any sort of intervention, let's just get this started and then see what happens. So as you can see, you have this susceptible strain growing, and it's actually one resistant strain. It's 2, it's 3, and it's 9, it's 11, it's 12, and then it sort of goes on and on and goes on and on. I'm just going to speed this up. This is going to be an intense Brownian motion. So we're going to speed this up, and okay, so it's still going on. So our first experiment, I'm just going to go here and I'm going to write, I don't need all of these. I'm going to write experiment 1. So what's going to be the percentage of resistance? That's what we're going to be writing here. The percentage of resistance strain that's present in the population once it hits 4,000 frames. So it's completed. So we have 2.3. So let's just write this here, 2.3. This is the experiment condition 1, and this is just sort of the default settings. So that's just a default setting. So we're going to do experiment 2. Actually, let's just keep this simple. Experiment 2 is going to include, it's more complicated. So experiment 2 is going to include, it's more complicated. So what is more complicated? What is more complicated is the fact that there are other additional sort of biological factors or biological variables that impact how these population dynamics tends to flow. And one of it is this conjugation. So conjugation simply the plasmid exchange rates, right? So resistant cells can actually pass resistance to nearby susceptible cells via pilus, and you're going to see that in the simulation soon. So this is going to be a bright magenta color, I believe. So we are now starting this experiment too, and again, I'm just going to speed this up. Again, this is going to be a very chaotic Brownian motion, and of course you can see this is not meant to be a perfect simulation. This is just to give you an idea of some of the logic. And if we sort of focus in, then you begin to see this magenta color, and that's essentially indicating this transfer of resistance from the resistance strain to the susceptible strains rather. So the transfer from the resistance to the susceptible strains. Oh, okay. So our experiment is set up to, and in this experimental condition we have a limit of 4,000 frames. So we'll see how many what percentage of resistance strains do we have after this point. Okay, so it looks like it's 33%. I'm just going to write that down. 33%. Our last one is just going to be everything above plus, let's say three antibiotics. Let's put 3 antibiotics. Let's put 3 antibiotics. So we're gonna start this experiment again, and I'm going to just say 1, 2, 3, and a few things. I think I talked about conjugation previously. I don't think I mentioned about the fitness costs, but the fitness cost essentially is there's a metabolic cost to resistance. So resistant cells sort of divide this time slower compared to wild type, okay? And then of course there's this gradient, this halo that you see around the antibiotic Dix. Essentially this is kind of like the stress halo that accelerates the mutation in the susceptible bacteria that are actually present in that area. Okay, so our experimental condition is set. Let's just pull this off and see what happens. Again, I'm going to just speed this up so this thing goes up. Actually, instead of speeding it up, let this cook, like the kid says this. But there's a method section right here that people who are interested can actually use. That actually goes into some details of what's actually going on. So the details of how the simulation updates, what each controls, actually the base controls, the details about the base controls, the details about the advanced mode, and I also talking about some of the main limitations of this because this is just a toy example. Mutation rates is, for example, intentionally inflated here for visibility. Resistance is not binary. It's more complicated than that. Cell movement is not random mixing, again. So all of these limitations I try to list as much as possible. Okay, so let's see. Looks like our experiment is still going on. This is the third experiment. And actually, let's now increase the motion so that we get to the point quite faster. Already, we have we're noticing that the populations of the resistance already is higher than the population of the susceptible strains. So 71%, 71%. So this is kind of like just a directionally accurate presentation of what these antibiotic pressures could look like just using this simulation. Thanks for watching.